A chip is not defined in isolation. It has to go into a system. We have to look at how many peripherals should be attached or attachable in this system. Every square millimeter of die area on a chip is incredibly valuable, and not just in terms of manufacturing costs, but also ongoing power consumption. And so every little detail gets scrutinized, and that's where the hard work is, building something like this.
Welcome to Nerd Out at Spotify, where we bring you behind the curtain of the world's most popular audio streaming subscription service. Machine learning, open source, clouds, tabs versus spaces. We'll talk to Spotify engineers about interesting tech issues, big and small. I'm Dave Zalatuski, principal engineer at Spotify. Spotify is migrating our compute to Google's new ARM-based Axion processors, upgrading the main chips that run all of our software from our current x86 architecture-based chips. This move will lead to cost savings, cut emissions, and improve performance all at the same time. And ARM isn't a new thing. We're all surrounded by ARM-based computers, including the ones in our appliances, cars, and smartphones. But it's recently been making the move to data centers and changing the game. Today, I'm talking to Mo Farhat from Google's Axion team. So let's go talk to Mo and learn about what goes into designing, building, and launching a chip like Axion. Well, hey, Mo, it's great to have you on the podcast. I'm glad you could join us. Let's get started. Can you just introduce yourself a little bit? What's your title? What's your role? What do you do at Google?
My name is Mo Farhat, and I'm a group product manager at Google Compute Engine. I lead a team of product managers, and we define the next generation of Axion and ARM-based virtual machines in Google Cloud. We build them, we launch them with our go-to-market teams, and of course we support customers in their journey to adopt them and see the wonderful results at the end of the day.
Tell me a little bit more about what that means that you and the team do day to day.
Sure. So first and foremost, we're talking deeply with a broad range of customers, really understanding what they're doing today with their compute infrastructure, how they're running their applications, their workloads, their databases, where they see problems and challenges. And we dive deep and make sure that we're building for them and to address them.
So tell me a little bit how you got into this role.
I started my career in engineering as a computer engineer and with an electrical engineering focus. I built laptops, desktops, workstations, particularly with focus on graphics cards, GPUs before they were called GPUs, if you will, at Dell Computer.
Back when the G stood for graphics.
Yes. And from there, I went to business school and moved into product management. Worked on enterprise storage, worked on cloud storage, two-tier, multi-tier memory technologies, for example, various different types of memory, and storage. SSDs that live in the server were part of my domain, and I was charged with evaluating all of these technologies and making sure that we design and build and introduce, only the ones that make the most sense for our customers. Of course, within a few months, my new technology focus was laser focused on ARM, and that consumed the last number of years of my life.
So let's kind of start at the beginning. Tell me exactly, what is a processor and why does working on processors excite you?
So a processor is the very core of a computer. It is the machine, a chip that sits in every laptop, every desktop, every phone, every server in the cloud that does the core operations that make the computer run. Things like multiplying data, loading data from memory, storing it from memory, transforming that data. What's incredibly exciting about the processor space is just how fast it moves and the reach of the advancements in processors. When processor capabilities improve, it improves the rest of the system, it improves the software, and ultimately all of the applications and cool things that customers do. And one of the coolest things I've done in my career working on processors is help Spotify move to Axion. It's something that I can relate to my daughter, and if it makes me cool in her eyes, that makes my day.
It's always great when we can work together on something that our kids think is worth our time.
So working on processors is incredibly exciting because the space is moving so fast. And when we make improvements to processors, it tends to have far-reaching implications, benefits to the rest of the system, the applications, and the things that people do every day, helping them do those things faster, more efficiently. And that efficiency is, I think, some of the coolest things that I feel personally about my work, that when we deploy more efficient machines at scale out there, it reduces humanity's carbon footprint and helps us all do the things that we need to do while taking better care of our environment and using our precious resources better. And it's just incredible to see that benefit, even though people may not be able to feel and touch it every day. I first got into the space as owner of new technologies in the server, and today is one of the most disruptive periods in compute in decades, due to no small part to the rise of ARM-based computing in the data center. And like all disruptive things, we want to make sure that we're solving the right problems, that we're not creating new ones, that we're making transitions easy. And there goes the art part of this, of course, on top of the technology and the science of it.
What was so exciting to you about ARM? Like, why did ARM specifically consume so much of your life?
Well, it was disruptive. And with change comes a lot of opportunity and excitement. And the change we're talking about specifically here for ARM is the long, successful history in mobile devices. ARM succeeded in mobile devices because it was incredibly efficient and gave customers and consumers longer battery life for smartphones, tablets, and today many laptops. What's new is that ARM no longer sacrificed performance for efficiency. And in fact, the latest generation of ARM processor designs based on the ARM Neoverse V2 core are matching and exceeding the performance of alternatives today, particularly in cloud-native workloads.
Tell me a little bit more about ARM, because I have a high-level understanding, but ARM is a company, ARM is an instruction set, and ARM is, I guess, multiple architectures of chip. Like you just mentioned Neoverse, and I imagine there are multiples. Can you give me a little ARM may mean one of these things, and when we mean it in this way, what is it kind of explanation?
Sure. So you're right. On the company side, I believe ARM's original name was Acorn, wonderful folks out of Cambridge. And the company evolved to the name ARM, which stood for Advanced Risk RISC. That's a Reduced Instruction Set Computer Machine. So this is an acronym on top of an acronym. So it was Advanced Risk Machines, I believe. And the company ARM built compute core designs that they licensed to companies that are building processors for phones, for example. And you can pick your example company. If they're building smartphones, they generally have ARM devices in them. They also built the instruction set that you mentioned. And today we're at version 9 of this instruction set. And of course, it continues to grow. We have instruction set extensions that do particular operations faster, easier for the developers. And ARM, the company, licenses not just the design of the compute core, but also the use of the instruction set itself if a company were to want to design its own compute core, which we see today in various places in mobile devices and laptops.
So tell me about Axion. First, tell me a little bit you personally. Like, how did you end up from that team working on ARM things and being excited about them, and now to be working on Axion at Google? And then let's talk about Axion itself.
Sure. The story of Axion started from the very core DNA of how Google builds their systems, hardware, data centers. Google started out building, stringing up servers in garages. And I believe more than 25 years ago, detailed out this warehouse scale computing approach. And this warehouse style scale computing is what it became ubiquitous data centers out there, and eventually became Google Cloud as well. As part of this immense scale, planetary scale, that Google Cloud operates in, we eventually hit problems that we just can't buy off the shelf parts to solve. And so we started building increasing portions of the compute, storage, and networking stack in-house. The racks, the server, the network cards, solid-state disks, and of course the final frontier of this is silicon and chips. And we, as you may know, for years now have been building our own AI accelerators, what we call tensor processing units, or TPUs. And those systems power AI workloads, Google Search, Photos, and many customer workloads out there. And we learned a lesson from all of this, that we can in fact get incredible efficiencies if we build what we need exactly. So the next kind of logical step for us in silicon is the central processing unit, the general purpose CPU, and it's in every server out there. And we applied all our experience to that design. And so we selected ARM as the architecture for Axion. And this was the intersection, if you will, of the growth of Google Cloud and the growth of the ARM architecture got us to this point where today Axion is the highest performance machine in its class available.
Well, so tell me a little bit more about that. Like, how is building a chip like Axion different for Google than building a chip like a TPU?
Well, much of this goes down to workloads and what the chip is expected to run, what it's optimized for. Google is one of the largest operators of compute infrastructure in the world. So we have very deep insights into what a cloud-native application needs, what a database needs. We've built incredible databases like Spanner and analytics capabilities with BigQuery and other services. So that helps us design not just a chip, but really the entire system around this chip.
It sounds like technical process isn't that different. It's really just that you're targeting very different use cases and the chip does different things. So it ends up differently, but it's not like you use, different tools and different manufacturing processes or whatever.
No, the manufacturing process, of course, is ever evolving, particularly in semiconductors. Intense pace there, but pace that's really delivered incredible advances and benefits, for the world. It's not about just the chip itself. Yes, there's industry tooling on this. You can have different approaches to building these chips. These are what are so-called systems on a chip. And so it's not just a compute core. There's a fabric that connects the compute cores. There's memory controllers. There's peripheral controllers, PCIe controllers, various management capabilities. So these are complex. And so in some areas, you might, in fact, reuse the same parts of the chip across different kinds of chips. But to zoom out a bit, the hardware is really just dead weight without the software that runs on top. And it takes a village there too. It takes an entire ecosystem, particularly as you're approaching something as disruptive as a new core compute instruction set. You need a lot of software to work together, a lot of middleware. And this is where Google's contributed. We've open sourced Android, we've open sourced TensorFlow, we've optimized Go for ARM. And we've also benefited, of course, from the incredible work of many developers out there, both in the open source community and at independent software vendors.
Yep. So tell me a little bit more about why this particular change is such a disruptive one that Google needs to help so much across so many different kind of layers of the software stack.
It's because the change is so foundational. We're not talking about a bathroom remodel, if you will, where you can have a localized change. We're talking about literally the foundation of the house. And when you move the foundation, you generally have to rebuild everything. That journey is mostly behind us. Now, ARM is a wonderful house today that is easy to adopt. I believe more than 80% of the CNCF projects are ARM compatible today. And certainly we at Google here have thousands of applications that are currently running on Axion. There's always a certain amount of uncertainty when you go about adopting a new core architecture like this, but we've been pleasantly surprised how easy the journey has been because of the work of the ecosystem.
Yeah, we certainly have been, but I guess more specifically in the actual SDLC, the process of building the software and deploying it and getting it done, all that. Why is this such a big deal? We've had, hundreds of processor changes, Intel releases like Pentium, whatever, 1 through 4 and Pentium Pros, and there's a new Core i something all the time. And we just swap those and it works fine. And then we get a new iPhone with a new iPhone chip and it just runs iOS and we're kind of fine. Apple even switched from PowerPC to Intel to ARM and things kind of just worked. So you say it's just a foundational, it's the foundation of your house sort of thing. What does that actually mean within the SDLC, for an engineer building that software?
Yeah. So in the examples you provided with laptops, Intel processors based on the x86 instruction set, or phones based on the ARM instruction set, those have been long-standing architectures in their spaces. What's different here is that now we're kind of cross-pollinating here. We're bringing in ARM into the traditionally x86 space. And what that means for software developers as they look at building software for the ARM architecture at scale with modern practices today is that they would need to build a new pipeline, a new CI/CD, continuous integration, deployment pipeline that takes their code and generates both ARM and x86 compatible binaries that give developers and companies the flexibility now to deploy on any architecture to best fit the workload or best fit, availability or any other considerations. Once you have built that core pipeline and infrastructure, maybe you could tell me a little bit about your experience in there as well. Generally, it just becomes part of the process with limited overhead on top of that.
I'm curious that on the other side, as a PM, what does a PM on a team designing a chip like this do? Because I imagine a typical Google PM might be looking at, features we need to add to Gmail or designs of something like Gmail. You don't really have a UX surface that you're trying to tweak. So what does a PM on a chip do?
Yes. So I guess the UX surface for a chip is the instruction set and the connectivity that provides to the rest of the system. But for semiconductor product management, just an incredibly intellectually stimulating exercise. Right? It's like looking in a crystal ball that's foggy. And, it takes 2-3 years to build a chip. And that chip will then live on for 5, 8, 10 years. And so that crystal ball has to look 10 years ahead. So there is a tremendous number of considerations that a chip product manager takes into account, working, of course, very closely with the engineering community hand in hand, the architecture community and the industry as a whole, because, of course, these chips have to be built on a certain process, semiconductor manufacturing process, that defines a lot of the capabilities, the power envelope, the performance headroom. And so it's somewhat of a layer cake. to first identify the kind of core performance by workload points and incorporate new capabilities, features. You saw, for example, a bit of a leap when we first saw, what do they call them? Neural engines or AI specialized components of a particular chip. The product manager that led the organization to decide to include that capability had a pretty foggy crystal ball there because the software wasn't there. It didn't know quite exactly how important it was going to be in the future. But sometimes you also have to take these leaps and plan for success and build around them. These are, some examples of kind of the decisions. And then, of course, again, a chip is not defined in isolation. It has to go into a system. We have to look at how many peripherals should be attached or attachable in this system. Every square millimeter of die area on a chip is incredibly valuable, and not just in terms of manufacturing costs, but also ongoing power consumption. And so every little detail gets scrutinized, and that's where the hard work is, building something like this.
So now that you've laid that out for me, like what were some of the decisions you made around specific, things you do or don't include on those dies, or what you want for the performance to be in specific use cases? Or like, tell me what makes Axion special and how you guys went through that product process and made those decisions.
Sure. First, it's core capabilities. And second, it's ease of use for customers to be able to adopt those capabilities. And those were deliberate decisions from the beginning. And first, Axion is the first of its kind. It's Google's first custom server processor. And so we defined it to deliver efficient, high performance. And then, of course, the ease of use aspect is the compatibility. Is a deliberate choice to build on standard ARM core designs because Axion is not the first ARM-based chip. And we wanted customers to be able to quickly build on all the ARM-compatible software out there. And if they had a ARM virtual machine image, which is a set of files and perhaps an application on it that run on the virtual machine, that they could just move this image over if they were running it elsewhere on another ARM server, and then again immediately get this kind of experience with, hey, it runs quickly, seamlessly, and I'm getting better performance than I had in the past.
The ease of use thing, I guess, it still confuses me a little bit. In my maybe naive view, would assume that any chip that is an ARM chip that just kind of properly by the spec responds to the ARM instructions can run any piece of ARM software. So regardless of what you did within your core choice, it would still be kind of the same for me as a user. I just run an ARM VM on my ARM chip and it works. Is that not the case? Were there like decisions you had to make about compatibility with ARM software?
Yeah, so you're right. Software built for a given version of the ARM instruction set should just run on another machine that supports that ARM instruction set version. But the devil's in the details, as they say. Cars have steering wheels and maybe back in the day, manual shifters. The way the engine acts, the way the engine runs the car is different. There's a long list of differences in what's called the microarchitecture of the CPU. Things like TLB sizes, depths, things in the fabric and how compute cores are connected to the fabric. It's not whether it just runs, it's whether it runs great out of the box.
Yep. What's a TLB?
Sorry, it's a translation table. It's a translation look-aside buffer. Basically a memory space that translates between physical memory addresses that the memory chips see and virtual or logical memory addresses that the applications see. So the application doesn't have to worry about where exactly its data is being stored on the physical memory. And the whole point is to make it easy for developers to access memory without worrying about the underlying system.
Are there like a lot of other things where if you were to compare, let's say, another manufacturer's ARM chip in a data center to the ARM chip in my laptop to the ARM chip in my phone to Axion? Like, what are the major vectors in which those chips would be different from each other? And the things where you really had to make decisions, like, I don't know, core type or something else that's just going to be blatantly different between like a smartphone and an Axion?
Generally, we care most about the items that are exposed to customers, the UX surface area, as you mentioned. All right. For example, the ability of the machine to give you a kind of a size that you expect while maintaining the performance and security isolation. Other items, or for example, the way you access the machine, the fact that it supports all of the various management capabilities, in the virtual machine space, for example, it's, resizing a machine or moving a machine, scaling it up or down, deploying it, shutting it off, like all of these type of user-facing capabilities, generally you want to be the same. Beyond that, it's really balancing what we call power, performance, and area in the design itself. That's the primary consideration when you look at a new processor design. Basically, how to optimize that, how to get the most performance, the lowest power in the smallest area. And then, of course, it's the decisions on whether to put in specific accelerators. We talked about the neural engine in the past, but, to take, given slice of silicon area and say, I want to use this to go and make something faster, even though many of my customers might not use it.
And I guess outside of these kind of purpose-built accelerators, are there other kind of obvious, like, do I put this thing on the die or this other thing on the die type decisions you have to make?
The biggest item there is probably the memory interface. So how many so-called memory channels will the chip support? And that defines how much data the chip can take in at a given time. And so this is part of a system balancing exercise of making sure that the chip has all the data that it needs to maximize the amount of performance, that it's not sitting there waiting or idling for data. The primary case there is for memory, then storage, the number of PCIe or PCI Express lanes that you build into the chip. And these all take very valuable space, particularly when you need to connect the chip to the motherboard. You've got some edges there that it's very limited space, and you've got to go route into kind of connectivity through pins and what have you. So there are a number of considerations. There are costs for investing more into these spaces, and you want to make sure you have a balanced design.
Yeah, cool. No, that sounds like a super interesting project. Can you tell me a little bit about future things? So Axion exists now. We have a whole bunch of C4A VMs we're all running. What are you guys kind of looking to in the future?
Well, the future is exciting. While we're in still relatively early days for ARM-based computing in the data center, we're at a real tipping point here. Some industry analysts say that ARM is going to be about 20% of server shipments by 2027. Our partners are ARM are even more bullish, and they should be. Regardless of where the exact number is, the trajectory is clear. ARM is going to be a bigger and bigger part of computing. And for us, as Axion, of course, and Google Silicon in general, we are investing heavily in both the custom silicon and the vertical integration of the silicon, from the service to the silicon, as we say. So so that integration will continue to improve. And then, of course, at the chip level, we've got advances in manufacturing technology, advances in the instruction set, various acceleration capabilities, and so the future is bright there towards more capable, more performant, more efficient chips. And of course, at the system level, nothing stands still there. This continuous integration, our titanium system, which is really our secret sauce here, is a system of custom tiered offloads that basically act like a group of super smart assistants for the CPU that relieve the CPU from having to manage networking or manage remote storage or various other aspects of the server operations. And those assistants are going to get smarter, grow in number, and they'll handle more and more work that, again, will free up Axion to deliver even more performance to the end user. And, industry developments, right? Like today, when we look into the future, you can make an argument that cloud providers, the largest ones, we call them hyperscale cloud providers, are driving incredible innovation today in the processor space. And this competition drives innovation. It's great for customers from performance and cost side. And it's really the future of where the cloud's going. And leaving us in a clear direction today. I mean, if you're running in the cloud today, the time to take Axion and ARM seriously is now.
Yes, I think that is very clear. Cool. Well, thank you so much for coming on, Mo. It's been a lot of fun having you here.
Thank you, Dave. Thank you so much for having me on and your partnership in general. It's been really great working with you and the Spotify team.
Tell me, outside of all of this awesome work with Axion and ARM, what else are you nerding out about?
Well, AI. It's just incredible, the new capabilities that we have access to today. I'm spending some time rolling up my sleeves there, working with AI to build some hobby applications. I tried to build a virtual pinball game. It still work. Definitely still need developers out there, but that's taking up a bunch of my fun nerd out time on the side.
Thanks for listening. To learn more about Axion, check out the link in the show notes. And look out for our next episode to learn about Spotify's adoption of Axion. Nerd Out at Spotify is produced by Spotify's Sarah Tazari and by Seaplane Armada, who wrote our ARM-based theme song. I'm Dave Zolotuski. Thanks for nerding out with us.